Thank you. First of all, I'd like to greatly appreciate Melika and Patrick and others for organizing this workshop and inviting me. I was really excited about the prospect of going to visit you guys. I've never been, but then I realized that I had agreed to go to a conference in Golden Conference, and I'm there now. That was agreed on 2.5 years ago before the pandemic. So I have to fulfill my promise. So I regret not being there in person. So really, I signed in as soon as I can get up. This is 5 a.m. California time, and listen to the last two talks, which were great. So I'm gonna switch gears a little bit and talk about experiments. I think it was really interesting to hear Tonio talk because I was a graduate student when he was at MIT, starting as an assistant professor. And his expertise was, when he started, was synchrotron characterization and solar cells. And I was a DFT person who's had a deep interest in making GW work high throughput. And now, many years later, we've essentially switched place. He's done a lot of modeling-based materials prediction, and I have developed a deep interest in a lot of experimental characterization, which I'll talk to you about. The work that I'm going to talk about was contributed by a number of students and postdocs that I have been fortunate to have in the years at Argonne National Lab. And in addition, they were deeply informed by many of my experimental collaborators in different experimental modalities, such as electron microscopy from Berkeley, Northwestern, and UIC in Chicago, scanning probe microscopy, literature data, computer vision, data science, as well as a huge list of X-ray scientists, both experimental and some of them computational. The fundamental problem that I'm tackling with is what is actually there in the material. So I started as a computational modeler who like the previous talks, do predictions of properties, sometimes using DFT, sometimes using machine learning. And, we will have a lot of predictions and we will try to beg someone to make them and so on. On the other hand, I also worked in projects in which some processes were being observed in operando experiments, and we are doing the corresponding DFT simulations. And then we realized at some point that we are going on parallel tracks. When the experiments are performed, they get the data, and the data can be very rich. We're used to simple 1D data like spectroscopy or diffraction. Or 2D images, but there's actually, of course, 3-dimensional images, 4D images, sometimes 2+2, sometimes 3+1, even 5D images with additional degrees of freedom. So there's a huge amount of data that comes out of those experiments. But usually the problem is how to go from those measurements back to the 3-dimensional atomic structure of the material. And that's sort of the problem, sometimes called an inversion problem, inverse problem, a different kind than the inverse design problem that has been talked about. We're really trying to get from, because there is a many to one, one to many, if you go from left to right, one to many sort of right to left, one to many possible mathematical relationship between atomic structure and the experimental data. So that mapping is not trivial. Oftentimes it's underdetermined. Just from an X-ray absorption spectrum, for example, getting a 3D structure is probably impossible because there are many similar structures that give rise to a particular spectrum. So this particular holdup of interpreting the experimental data, doing the inversion of that data was a source of great frustration for many of us. Usually there's days or months that go by before we get some kind of fitting results. And that's not the fault of the experimentalist. We have the same problem in DFT simulations. We will spend months doing a simulation just to not really know if our starting assumptions were correct, our starting structures were correct. I got a fortune cookie, which was from a Chinese restaurant meal, maybe a couple months ago, and it says it is necessary, therefore it is possible. I quickly took a picture of it, as it is the trend these days, because it was so true. It is really necessary for us to do something about this bottleneck of interpreting characterization data from many kinds of sources. And this idea that, it's necessary, therefore it's possible, is it's very nice to think of, especially when we are tearing our hair out in frustration when the data doesn't comply with our wishes. So there are many kinds of characterization data inversion or information extraction. Like, what do you want to get out of it? What do you want to invert out of it? What level of representation do you have? That we have worked on, and I'm going to give you a few examples of them from various aspects: reciprocal space, diffraction patterns, or real space, very local electronic descriptors, or more full atomic structure from different types of experiments. Of course, I was trained as a theorist, so we still use a lot of theory and modeling. And of course, in all of those cases, the forward simulations part is critical, because if you are not able to take a starting structure and predict the experimental observation, at least to some degree of accuracy, then there's no way to tell if you've gotten the right answer for the inversion problem. So it's always the case that we start with the forward simulations and work on that until it's acceptable. Acceptable is also something that has to be negotiated, between the modeler and the experimentalist, because there's a lot of nuance and subtleties involved. Of course, we also use theory to provide a lot of training data, all sorts of different atomic configurations, which ones are reasonable. We use DFT, we use force fields, and then we generate them using the whole richness of atomic structure searches that have been in the works for 30, 40 years. And with that, we also can apply some constraints into what atomic structures are reasonable. Now, everything I'm going to talk about has to do with atomic level information. That's because of the tools we have. But you can think of an analogous problem in the mesoscale. You can talk about microstructure, in the same way. And I know there are other people who work on that. So let's talk a little bit about forward simulations. One of and Patrick here is an expert in this. One of the questions we have is, how accurately can we simulate core level spectra, such as the X-ray absorption near spectra SANES, or electron energy loss spectra EELs? Here we did some practice with the ocean code, which is a beta sub beta equation code. And we did some work helping the developers, which were John Vincent and Eric Shirley at NIST, to make the code more user-friendly, and benchmark it on these system transition metal oxide K edges primarily, but also some L edges, and found reasonably good agreement. Since then, we have actually benchmarked a large number of different codes for particularly transition metal oxide system. And it is, as much as I would like to say that there's always one code, one approach that you can use to give you satisfactory result, that's not what we have found so far. We found in different problems, we tend to need different codes for that. And that's still a hurdle for more widespread automatable or even autonomous inversion of these type of data. So in X-ray spectroscopy, core level spectroscopy, we try to get it close to experiment. In electron microscopy, the opposite is true. If the simulation approach for electron microscopy is actually, well, we still want to get it close to experiment, but not in the same way. The method to simulate electron microscopy, namely multi-slice approach, has been around for a while, and recently Colin Office has made an improvement on the speed of the code with its PRISM method. The problem, however, often is that the simulated image is too clean, is too perfect, whereas experimental images don't look like that. So we actually worked with Colin, my student Eric, to apply the appropriate type of noises on the simulated data so they look like experiments. Our triumph came when Eric gave his thesis defense, and there was a respected electron microscopist in the audience who was pointing to one of the figure and specific parts of it and said, we can't really take this seriously. There was a machine artifact. And then we were smiling because those were actually simulated images. So, of course, the test is when you can actually fool a real practitioner that this is a realistic looking image. Of course, probably nowadays you can use DALL-E or other things to do something like that. But I don't know that on a statistical level, something DALL-E generates will be accurate. So if anyone's working in this area on microscopy images, we have put out a set of 60,000 images that are simulated with different levels of appropriate noise. If you want to play around with it, train models on it, it's on this GitHub. So having talked about the forward simulations, let's talk a little bit about inversion. One of the problems had to do with reciprocal space information diffraction patterns, and that comes in the case of 4D STEM. Again, this was a collaboration with Colin. 4D STEM is 2D plus 2D, is two-dimensional scan rastering of the electron beam. And at each beam position, you get a seabed image, convergent beam electron diffraction pattern. It looks like the image on the bottom. It looks a little bit like a diffraction pattern as we are used to, but not exactly, because there is a thickness of a sample and multiple scattering, so it's not kinematic scattering unlike XRD. So what happens is some of those disks can be overlapped and sort of distorted. So one of the tasks that we first need is to turn those into Bragg positions and intensities, and then use that to try to invert and find the atomic structure corresponding, crystal structures and strains and so on. So the approach we used was to simulate a very large number of seabed images, and then train a convolutional neural network in order to carry out the mapping between the seabed image and the Bragg dispositions. So we need one model to work for everything. So we need to have a large selection of materials, and we did that using materials project database. But we don't want too many duplicates or similar structures, so we use actually the crystal structure prototypes from AFlowLib. In addition, we also try to balance out the atomic mass distribution because they affect the scattering of the electron beam. So we want to represent different atomic numbers. So with those training data, we then started to train different networks to see if the results are good. We started with the more obvious choice of a UNet, and then got reasonable results. But then we realized that we were working on this problem where we were looking at a reciprocal space image, but the symmetry is contained or is there in the real space image. And we try to see if we can incorporate some of that in. So we actually use a Fourier transform within the neural network and carry out complex convolutions. So there's real imaginary parts in this. So because it's a Fourier complex UNet, so we call it FC UNet, that actually gave much more accurate results than the simple UNet. I'll give you some examples here. On the top is an easy case where the seabed image almost looked like a diffraction pattern you would recognize. You can draw, with some intensity thresholds, you can draw the Bragg positions. In fact, a previous approach, which is called correlation, can do that. Using deep learning with the FC UNet, we improve the accuracy by a bit. But the remarkable cases come in something like this, where there's no chance for a human to pick out the Bragg dispositions. And in fact, the correlation approach has completely failed, but the FC UNet still does a reasonable job. So that was what we published recently. With a tree model like that, we tested it on strain maps in real experimental data. So this is still, it's a sort of an artificial setup, the silicon germanium layers, and these are the seabed patterns. The dispositions obtained from correlation shown on top, and the dispositions from the FCU nets on the bottom. With that, we can work out the strain, and these are shown here, because the ground truth for the strain is obtained from eels, because the silicon germanium, we can work out the concentrations and deduce what strain to expect. And then the strain found from correlation is shown on top and from FCU nets on the bottom. These are the profiles. You can see that there's a bit better accuracy with FCU net and the direction where you expect strain, and also slightly better direction where you don't expect strain, which is the vertical direction of this. So just to summarize, this is sort of one type of information extraction. We take one step of the analysis forward. This is carried out with a large number of simulated training data, 200,000 training data. One of the advantages is that it improves on the accuracy across different crystal systems. Previously, some crystal systems would work better than others. Sorry about the spacing here. Something missing. Some crystal systems work better than others, but with the FCU net, it seems that we have more even distribution. So this came out end of last year, beginning of this year in MPJ computational materials. So that was reciprocal space, and now we move forward quickly to real space, and I'll be brief in that because I think people are familiar with this. Electronic descriptors, very local descriptors from X-ray absorption. X-ray absorption tells you the local environment of the absorbing atom. In the cases that we have studied, they involve things like oxygen atom in a lithium battery material that undergoes a lot of reorganization, even oxygen evolution. So we're trying to pick out whether the oxygen is turning peroxide, whether oxygen has a lot of transition metal neighbors or purely lithium neighbor, which is conducive to oxygen redox. So in some other cases, we look at transition metal oxide, traditional lithium battery materials, and look at the number of lithium neighbors for the transition metals. That tells you a little bit about the local state of charge, which is useful because when a lithium battery charges and discharges, it's not always even. If you can do things mapping and deduce local state of charge, that will be interesting. In another case yet, we looked at a dopant in a semiconductor solar cell material, cadmium telluride. So X-ray absorption really shines in these kind of situations because the dopants are there in parts per million or even less sometimes. And other techniques would completely not be able to see it, but because X-ray absorption is sensitive to a specific element, we can pick out dopants such as copper and arsenic in cadmium telluride, even when there's very small amounts of them. In all those cases, we almost carry out a very similar approach, do a lot of structural configurations using density functional theory, calculated spectra using different codes, and try to figure out which code does the best in matching a few reference spectrum. And then train simple AI models or ML models, such as a multi-layer perceptron or random forest models, and then compare the predicted coordination number to the ground truth, which is what we did in DFT. So the three examples are shown here: cadmium telluride solar cells, copper as a dopant, the number of nearest neighbors for copper, lithium iron oxide battery, the number of iron neighbors for oxygen, and NMC batteries, number of lithium neighbors for transition metals. You can see that we use different simulation codes, both a balance of accuracy and cost, and different machine learning approaches. The results are actually really similar. We find that there's reasonable accuracy, maybe 5% in a coordination number, maybe 8% sometimes. The machine learning approach actually didn't make a huge difference. Of course, the transferability of this model to experimental data, which is not shown here, is greatly dependent on the accuracy of the initial simulations, as well as somewhat dependent on the representation we use. So that's the whole another talk we can give, but I'd like to move on in the interest of time. The next type of problem we deal with have to do with microscopy. So for many years, we're working with microscopists, electron microscopists and scanning probe microscopists. And then we realized that there's a need to determine if a particular structural model matches a microscopy image. That was something that was very labor intensive for a while. We literally simulate microscopy from a structure and try to match it with human eye. And then that led us to ask the question, what is a good metric to compare similarity of two images? And that wasn't a trivial problem. We worked on that. And then eventually we developed this code called Ingrain. Eric, again, was my student, and Chaitanya also was a postdoc who worked on this. So the problem that Ingrain solved is that when you have a microscopy image and you want a matching simulated image, you can use Ingrain. Here are some examples. The reference down here, if you want to see the actual details. Here are some examples for electron microscopy. This is on the left, it's experimental image. On the right, it's a structural model. In this case, in the middle, you see the simulated image. You can see if you're familiar with modeling, which you are, that there's something wrong with the interface, that the interface is not quite physical, and that's what's going to be solved in the next code. But Ingrain does a rough matching of the top and bottom part for interfaces, and try to have a periodic structure, which is important for carrying out further simulations. And then in this case, it's a NMC battery. On the left, it's a cadmium telluride interface. On the right, it's battery material interface. These turn out to be enormously useful because we are so often faced with a question of deducing some physical properties of some material interfaces. And the fact is there are so many interfaces we can make as modelers, and not all of them are realistic. We can calculate interface energy, but that doesn't account for all the conditions of synthesis and so on. So having a realistic model based on an experimentally observed interface actually was really powerful. We extended that to scanning tunneling microscopy, STM, where there's an additional problem because even when you have the same structure, so this is a surface now and on an interface, even if you have the same structure, because STM probes not the atom directly, but the electron density isosurfaces, essentially, or tunneling probability, really, the potential. There's a lot of different images that you can get for the same surface if you apply different parameters in the simulations. So Ingrain additionally added that optimization for the simulation parameters. And you can see here as an example of a surface from Mark Hersum's group at Northwestern. Experimental images on the left, it doesn't have to be perfect. The simulation looks at a smaller patch of it, and then Ingrain carries out the simulation, as well as look at the optimization of the parameter, and which part of the experimental image fits that simulated image best. So as you can see, when the similarity progresses, at the end, it kind of looks like it almost melts into the experimental image. So that was a very nice example, and it was fortunate that Mark Hersum needed that answer to that question, and we needed a tool that answers that question, because this was the structure of the animation I was showing you was a structure of hydrogenated boron, or called boron. So boron is single layer boron, which is very different from graphene and silicene and others, because it's a metallic, and boron really doesn't necessarily prefer a 2D structure. But anyway, Mark was able to hydrogenate it in the first step towards trying to isolate it electronically, and maybe induce a gap at some point. But the structure was not very clear, especially from STM alone. So with Ingrain, together with a lot of deep sea simulations, we also simulate things like vibrational spectroscopy to validate this structure. We find that the hydrogen sit on 2 different sites, and boron is both cation and anionic in different parts of borofane. So that was really interesting and different, and that was on the cover of Science a couple of years ago. That gave an approximate atomic structure, but really our holy grail is to spit out the 3D atomic structure from experiments as widely varied as X-ray diffraction, reflectivity, paired diffusion function, X-ray absorption. I said it might not be possible with X-ray absorption alone, but what if we have XRD and XAS? What if we have Raman and XAS or other combinations? So this push towards doing multimodal experiments has been there for the past 10, 15 years. Progress is slow, but we're slowly getting there. A lot of times it's practical issues with the sample. In one particularly notable case, where we were trying to, our experimental collaborators were trying to do XRD and Raman on a synthesis process. The crucible exploded repeatedly. So those are the kind of problems they have on the experimental side. But on the modeling and interpretation side, we also have an issue where the data is not always available sort of in an equivalent way. So we're trying to work on this with this code called Fantastics, which stands for Fully Automated Nanoscale Atomistic Structure from Theory and Experiment. The lead developers are Chaitanya and Davis here. In this name, Fantastics, the fully automated part is still an aspiration rather than reality, but that's our goal. So that we can have a structure comes out of the experimental data in semi-real time, maybe not immediately, maybe in minutes or hours. So the approach for Fantastics were built on what we've talked about in this session. We need modeling to give us some sort of approximate Hamiltonian, either DFT or interatomic potentials. So the recent development in machine learning potentials is really exciting to us. We are implementing ML potentials into Fantastics just to speed it up. And then the other part is forward simulations, which I've talked about, and match experiment. That involves both simulating an experimental signal as well as having a good metric to compare them. And that's not a trivial problem. The other part of it is generative model, as Tony will talk about it, how to come up with new suggestions for the structures. Of course, we use a lot of genetic algorithm based on Alpine Monte Carlo. One of my postdocs working on graph neural network approaches to create new structures and try to examine the coverage of the structural space, which is very high dimensional. So all of this work in concert. We didn't develop brand new codes for simulations always. Some of the existing codes that are in the community, we build workflows to work with them. Similarly, for energies, we build workflows to work with VASP and LAMPS. And the generation of new structure prior we work on. So all of that work in concert. And here's an example of Fantastics in action. It's much easier to see a microscopy example, so that's what we used. It's almost one of the easier problems that Fantastics deal with, which is turning a 2D TEM image or SEM image into a 3-dimensional structure. So we start with a clean interface that comes out of Ingrain, and then sample the different interfaces, and then at each step simulate and carry out a comparison, evaluate the metric of image similarity. Both the energies and the image similarity go into the cost function. We have single objective or multi-objective options, and then that allows us to survey a large number of structures. And you can see at the end, here's what I mean by there are a lot of possible interfaces. So this was a real interface in a CATL solar cell. And this is something that it's very messy. It's not like a clean sigma 3, sigma 7 grain boundary. It's not something a modeler would routinely come up with. So that's what I think it's important to really look into what's there. So with Fantastic Developed, we took one of the previous examples we worked on. This was a single layer of tellurium sandwiched between cadmium telluride. It just formed by itself. It was really interesting. This to find this the model that fits this by previous methods, a lot of hand tweaking, staring at it, using intuition. That took a few months. And then once Fantastics was developed, we gave this image, and a couple of days on the cluster, it found, and not even that many structure was sampled, and it found the correct structure. This was a rather simpler interface, but still, I think that the time saving is there. In other cases, on paired distribution function, X-ray paired distribution function, I remember this example because I talked to the postdoc. We weren't on the same project, but he was tearing his hair out on fitting this PDF, and the fact that you can you start with a rutile structure of iridium dioxide and tweak the positions of the atoms. You can get a good fit, but then there's a lot of, again, back and forth manual fitting, and then also starting with a very biased starting point, which is rutile. Instead, in Fantastics, we threw atoms in a box. We had sort of a pseudo-amorphous type structure, which is still periodic, but a biggish cell. We let Fantastics run with a multi-objective approach, which balances both the fit to experiment as well as the energy of the structure. And it found the structure again, maybe a week or two on the cluster. Most of that waiting for computer time to run, and then it found a slightly better fit in terms of chi-square. It also discovered some of the structures that wouldn't be intuitive for modelers, such as this 3 oxygen bridge between iridium, the 2 iridium. So we find that promising. In X-ray absorption, the fidelity of the simulation is always a problem. We never get as good with XAS as many other things, but still, because there's a severe constraint with DFT on the structure, we were able to find this transition metal complex using an XAS that only roughly matches. And XRD, again, there's a lot of work that has been done already on XRD using neural networks. In all of those cases, you need to have, in almost all of those cases that I have seen, you need to have a set of XRD patterns in your library. If you talk to people who do XRD in the beamline, they'll say that's usually fine, but every once in a while you have a problem where you need ab initio structure, and I was curious what they meant by that, and then they actually meant like you didn't know the structure at all, it's never been seen before, you need to find it. So we don't have an example of that from experimental side, but we sort of took some XRD that are there and try to find the different structures from them. It's interesting because you can see that there are some structures that are very high in energy, such significant high in energy than others, and some of them that match the XRD better. So I think one of the power of this approach is we don't get one answer, we get sort of a family of answers, and you can do simulation statistics, and other analysis on them. So determining the structures is something that modelers understand to be important. Sometimes experimentals like, why do I need this? One thing that I think usually convince people that seeing is believing. You can, you see the transformation of the material under operando conditions, that really it's quite attractive. But on the material science level, you can do things like materials design. So with a realistic model of a grain boundary, you can put in different passivants on it and calculate the electronic structure changes. So, you can create all possible grain boundaries and, maybe all, not all, you can create 10,000 grain boundaries and do, and put in the whole periodic table on it and in 10 different positions. Or you can take the ones that are observed in experiment and do that. So I think that was a really nice method to do material design that's realistic and relevant. So that was published a couple of years ago. Another is in situ interpretation with synchrotrons now going through a lot of upgrades. Even before, you can get 1,000 XRD patterns. You can get 10,000 XAS from a mapping. So being able to do automated interpretation and on a large set of data without human bias, I think that's quite useful. And then finally, as I mentioned before, we can carry out modeling. So in this particular case, this was an NMC battery material. And we were trying to understand the oxygen stability of this material. So in batteries, one of the problems is when you charge it to very high voltage, oxygen sometimes becomes unstable. And our collaborator had a hypothesis that the interface is a particular vulnerable point. So we carry out simulations of this oxygen removal energy, particularly at the interfaces that are experimentally observed, and find that indeed it was significantly easier to remove oxygen from there. So this was published last year. So all of these examples show that having a real structure allows us to have deeper understanding, more realistic modeling, and so on. So I think this direction it's been fruitful so far. In the process of working on experimental data, it's not like Nomad or Materials Project. There are bits and pieces everywhere. And I have this experience so many times that I would talk about something and show some data, and then someone will show say data, and a very experienced experimentalist will say, I've seen this before, this means XYZ. And I think this is great, I mean, that's why humans and experience is important. But we also want to harness that. And one of the projects that we started working on is automatic gathering of experimental characterization data. So many people have been working on the language models, extracting information from reading literature using AI, and I think that's really exciting. What we started, this was 3 years ago now that we started this project, and the paper was just accepted in patterns like last week. This code is called XClaim, Extraction, Separation, and Caption-Based Natural Language Annotation of Images. We need to come up with shorter acronyms. XClaim takes images from a keyword search from figures in papers. It carries out this step of separating the figures, which was not easy because there's a lot of figures jammed together. You all know your published papers. And then attach the label from the caption to the particular figure, and also classifies the figures into things like microscopy, diffraction, plots. So we find that, hopefully that's a step that's useful towards aggregating the knowledge from the last at least 30 or 50 years, where people have reported a lot of different microscopy and spectroscopy and other things. The other part that was needed was to digitize the spectra. If we want 2,000 X-ray absorption spectra from the wild, that's not easy to get. Papers is one source of them. And in order to turn that into something machine readable, we need to digitize it. And so when my student also worked on plot to spectra, which came out end of last year in Digital Discovery, and it was more automated than things like WebPlot Digitizer, which some of you may be familiar with. So just to close, I think that in the future things will be a lot more integrated. I think Tonio showed a good example of working, sort of the crossover between theory and experiment and AI, and I'm showing you another aspect of it. The computational design bit is still going to be there. In our group, we do some of that as well. The synthesis part, which is, of course, really important. But at the same time, seeing what you actually get. So that comes in the form of digital twins, simulating the experiments, doing the experiment, inverting the experimental data. So as much of that that can be automated would be, really beneficial to speeding up this endeavor. So with that, I'd like to close and thank you for your attention. Talked about characterization data and turning that into structural information using a combination of modeling, AIML, more traditional structure search in computational modeling, and a lot of work towards building codes that can carry out some of this task in a more automated fashion, as well as extracting scientific information from scientific literature. So I'm happy to work with any of you who's interested. Please feel free to reach out. I like to acknowledge funding from the U.S. Department of Energy primarily, as well as the National Science Foundation. The computational resources came from the Center for Nanoscale Materials, DOE facility, Department of Energy facilities, and Argonne facilities. The Center for Nanoscale Materials is a user facility. It is open to users who are doing scientific research all over the world. So we have users from Europe, we have users from Africa, Asia, and so on. If any of the work that I'm talking about was of interest to you, we're happy to work with you as a user, and please feel free to reach out. So with that, thank you so much. And if you have any questions, I really love to answer them.
Thank you, Maria. I hope you heard the applause from the live audience here. So yes, the talk is open for questions. We're just bringing the mic to the person. If you have questions, the remote audience, if you have questions, please type in the chat.
Yeah, hello. Thank you for the really interesting talk. So when you simulate the STM images, the output image is really sharp, and you have to do this Gaussian blurring and adding noise and stuff like this. But how do you determine the amount of this blurring and this post-processing you do, or is getting that correct even relevant? That's relevant for the functioning of the final model?
Yeah, that's a great question. One of the sort of philosophical question is, should you denoise the experimental image, or should you add noise to the simulation? So we go round and round with experimentalists on this. But on a practical level, what we will do is, what we have done, actually that paper is still being worked on, is process the simulated image with different levels of noise. So you can add different background noise, Poisson noise, Gaussian blurring, and then look at different image similarity metrics. So we've used Earth move resistance, we have used SSIM and other approaches, and then see which approaches carry out the retrieval better. So, and which noise level is appropriate for the retrieval. By the retrieval, I mean, I start with a particular image, I know what structure it is. Can I match it, out of a bag of 10,000 of them? So the noise level that allows you to do a reasonable match, of course, you throw an experimental image to do that, a noise level and the similarity metric that allows you to do a reasonable match, that's what we use. But in the AtomImagined data set that we make available, there are different noise levels, so you can, play with it. Does that answer your question?
I think it did. Yeah, okay. He's nodding. Good. I had a question on your X-ray absorption example or machine learning workflow. So are you also forward modeling there to do the identification, or are you trying to map the signal back with a neural network. I think John Rea had done something a few years ago where they tried to learn the local environments and predict them directly. But the problem there was that the representation was not invertible.
Right.
So which direction are you going with that work?
So Fantastics now work for XAS to some extent, well, for molecular systems right now. Basically that would be like a generative model. I mean, we use GA at first, and then now we're adding graph neural network. You know, that's a full reconstruction. We also at the same time train descriptor based ML models, which are easier and faster, and sometimes suffices. Like for battery examples, you know, you don't always need the full 3D structure, right, of the local environment. You just need to know like a local state of charge, or some defect concentrations, or, you know, something descriptor based. But of course, I think the problem with the descriptor based approaches are that they are more specific and not transferable, right? You train on a particular type of system, and then, you know, you only work on those systems, which is good when you're very focused on one thing, but very difficult to make a generalizable tool. But Fantastics is sort of intended to be very general. So you can recreate any type of structure. And we have interfaces, we have surfaces, we have clusters, we have bulk crystalline. So, you know, that sort of covers a lot of things. We haven't tried, as you say, we haven't tried reconstructing structures from bulk XAS, but, you know, that's sort of on the list.
Hi, Maria. I had another question related to your talk. Thank you very much. Very impressive work. You've shown in your talk and also on this slide that you have access to many different experimental techniques, and you're trying to combine them all to infer the atomistic structure details. But now that you've done all this work, you also have access to all these different channels of information about the material. I wonder if you've ever considered mapping from one experimental technique to another, or from one material's response to another, without necessarily having to know the structure. So it's kind of bypassing your central problem and just going from property to property.
That's interesting. We have not done that. You know, like take an XRD and predict a Raman, something like that. That's interesting. I have not done it. We always go back to the structure because, I mean, this is our sort of inherent bias. As a modeler, the structure is valuable because with a structure, I can have an electronic density of state. With a structure, I can have a defect energy. You know, with a structure like that sort of gives me access to simulated properties that cannot be measured. And also you can see that, you know, all the work that in the preceding talks had to do with mapping from, well, okay, maybe not the thermogenic, but like Tonio talked about representing a structure and predicting properties from it. There are a lot of work in that space where you go from structure to desirable properties. So I kind of feel like structure is a good hub in a sense, not that there's, you know, in some cases no value in mapping from one type of experiment to another. But yeah, that's a really interesting thought.
I guess I'm asking because some channels are easier to measure than others, but they're often equally valuable. And if you could infer the mapping, then with less cost, you could infer the property.
Yeah, that would be really cool. So, you know, most things we forward simulate directly, but one work that I didn't show on here is we are actually trying to predict Raman with the neural network instead of simulating it, because it's so painful to, you know, get all the forces to zero and then calculate the phonons and then realize, oh, actually the forces were not zero. And I think many of us have that experience. So yeah, getting, you know, some of the more expensive or tricky experimental methods, experimental data kind of predicted one way or another, it's very useful. Yeah, you're right. Thanks.
Okay, I see no further questions here. So, but if they do come up during the conference and somebody asks us, then we relay them to you by email. Okay, thanks a lot, Maria, for joining, even if it was only remotely.
Yeah, I wish I can see you some other time. Thank you so much.
Enjoy your Gordon conference. Okay.
Thanks.
So this brings us to the end of the talk part of our workshop. We have a about a 20-minute break before the poster session starts, but they may have already set up the catering.